But we're going to move on to our next speaker, Justin Linker.
All right, so I'll say good morning, good afternoon, good evening, depending on everybody's location. I am Justin Licker. I'm from APL. You will recognize that I'm not Janet Green, our PI, but I'm pleased to be speaking on her behalf and on behalf of my colleagues and co-authors today. So you can go to the next chart, please. And so just introducing the topic here. So sustained operations, be it humans, robotics within the lunar system, so lunar surface, lunar orbit, cislunar space, so on. It demands reliable, predictive, verified or verifiable space weather capabilities with quantified or quantifiable uncertainties. So the goal of the interdisciplinary team, our interdisciplinary science team, is to better understand the variety of the environments encountered as the moon orbits the Earth and to characterize how the charged particle populations and the radiation throughout that environment affects the space systems. So results of this work will be prototyped into a space weather awareness tool to specify and predict the environment, its impacts, and the hazards to the space systems in order to support both current and future exploration missions. So this particular project, the title is Understanding, Specification, and Prediction of Lunar Space Weather, kicked off just recently in support of actually some of the projects that Bill was introducing earlier. So it's part of the Heliophysics, Environmental, and Radiation Measurement Experiment Suite Interdisciplinary Science Team Study. So it's an acronym. Bill introduced this earlier in terms of science goals, objectives, and I certainly don't have to do it here. But the purpose of my presenting today is really just to introduce this particular project, given that it's in a very infant state. So I'll give a brief overview and some objectives and early results. So for example, in terms of charged particle environments, we're seeing it here, just wind plasma, solar particle events, CMEs, galactic cosmic rays. We've heard about these and some of the fine features therein already. Um, here we're also showing some of the highly localized lunar surface environments, such as magnetic anomalies, dawn dust terminators, so on. Um, for example, permanently shadowed regions, pits, lava tubes. All of these offer very localized, unique environments into which humans and engineering may be operating, and all of these will require accurate space weather predictions. I think that the motivation is pretty clear. Um, in principle, the process of connecting the relevant particle environments to the relevant hazards is critically important in the success of this project. So if you'll go to the next slide, please. Our motivating research questions that are drivers include: one, what are the particle populations that present a hazard to astronauts and spacecraft or other engineering operations at the moon? Number two, how do those populations vary with time, location, and different driving conditions? Number three, how does the environment translate into the hazards or the impacts? And number four, how can we characterize and predict the environment and impacts and best communicate those hazards to the users? So our solution relies on the linkage between particle types and energies to the specific hazards to which they impact. And that's what we're showing here. In trying to summarize the relevant charged particle populations, you can see it there at the left, and the specific effect or the hazard associated with each. So you see it there in the middle. Um, including, and you can see spacecraft surface charging, lunar surface charging, internal charging, single event effects, and the cumulative effects such as total ionizing dose and non-ionizing dose. Uh, the specific location in the lunar orbit there, second column from the right, and lastly, the data sources currently in use and those expected to be in use upon Hermes launch and operation. Because I'm an engineer, I did want to take a step back and just briefly um, review these hazards in a little bit more detail and make sure that everybody is speaking the same language. So in spacecraft surface charging, lunar surface charging, here we're talking about the charged particle collecting on the satellite vehicle or other spacesuit surface, for example, producing high voltages, potentially arcs or so-called ESD events, also electromagnetic interference. Common worry items are thermal blankets, solar arrays, and so on. Internal charging, here we're talking about the accumulation of charge in the interior dielectric surfaces. Could be regolith, could also be ungrounded metal shields. Single event effects, here we're talking about charged ion passage through a single microelectronic device node, causing potentially instantaneous failure or nuisance type events. Cumulative dose, I think people are quite familiar with cumulative dose effects. Should go on to the next chart, please. Where I want to just kind of spend a good amount of time into the process we're going to use, specifically focusing on surface charging risk assessments. So this chart that it offers kind of a high level summary, but briefly up front we're focused on engagement with the Hermes instrument PIs. So Bill alluded to this earlier. The idea here is to ensure that the plasma data is not compromised by field of view or spacecraft charging effects. Prior to the launch, the effort's going to be focused on simulating what the particle distributions look like in different lunar orbital regions and developing corrections. Also, prior to the launch, we'll develop corrections to the plasma measurements to account for any spacecraft charging. So techniques here are based on algorithms used already for LANO, GOES-R type plasma instruments. In order to validate, we'll use, yep, yep, thank you. We'll use the collected data as plasma environmental inputs into the NASCAP 2K engineering tool, which we're showing a gateway model there on the top right. It's commonly used by engineers and analysts in assessing surface charging risk. So we'll compile simulated surface charging information from the data correction algorithms, and note here that this type of result is very, very dependent on correct material property specifications, which is another focused area of our effort. Moving on, we'll create a model of the expected and measured plasma environment and its space weather impact or hazard. So here we're talking surface charging potentials as the moon orbits the Earth. So prior to launch, we'll use Themis Artemis data. We're showing that in the lower left. To model the environment, we'll do both a statistical model and a neural network. Statistical model similar to what's used in the Disney with some updates. We'll use the Themis Artemis data to build the neural network using same plasma parameters. Once it's trained, we can then use it to produce a map of the expected plasma parameters at all the locations along the orbit. Once this is complete, it's then possible to turn the plasma parameters into expected spacecraft potentials. So to obtain frame and differential charging potentials for Gateway, we'll continue with a series of parametric runs, again using NASCAP 2K, you're seeing it there on the right. We'll also vary surface potentials to quantify resultant uncertainties in these potentials, also in material property uncertainties. The output there is essentially going to be a lookup table of frame and differential potentials along with quantified uncertainties associated with each combination of densities, temperatures, material properties. At that point, we can translate pretty readily from plasma parameters into charging levels and uncertainties and risk. And what you're seeing there in the lower right is a candidate display. So the idea is to display this in a manner similar to what we're seeing here. This happens to be from Space Hazard's SatCat tool, which is running now for GEO, but it will serve as motivation for the real-time and time history displays that we're talking about here. So finally, on the last slide, it's trying to wrap up on time. Yes, we understand we need reliable, predictive, verified or verifiable space weather capabilities with quantified uncertainties. The images we're depicting here, they come off as potentially mundane operations to be routinely carried out. So docking and rendezvous, for example, operation and service of photovoltaic systems. But each of these activities, along with the countless other activities, carry with them risk associated with lunar space weather, particular spacecraft charging. So as we know, the risk in performing spaceflight operations is assessed in terms of likelihood and consequence. So this is successful completion of this project and others, and the development of prototype space weather awareness tools will enable shareholders to monitor such risk, make informed decisions regarding their critical operations, and also troubleshoot anomalous performance. So I thank you for your attention.
Awesome. And as Sabrina noted to me, this is a fantastic slide to end on, and I think one that helps us kind of start looking towards the future and the idea that we can prototype a lot of these systems on the moon where we still have SHRAG and M2M and others who are able to confirm what the space weather is looking like. But by being able to prototype and use these here on the gateway and at the lunar surface, we're going to be able to prepare for Mars when we might not be able to have that human in the loop. So before we go to the closing remarks, I would love to invite everyone to unmute and thank our speakers for the afternoon sessions. This has been absolutely fantastic and such great questions and talks throughout the day, let alone the afternoon sessions. So please join me in thanking our speakers.
Thank you.
Thanks, everybody.